My second time missing it.
Bye, guys.
Nope. Yeah, you hang. I got on just in time. Okay. Oh boy. I've been having trouble this morning with my internet time. It wasn't Alexis that was frozen. It was my problem. Hang on.
Don't worry, I sung a beautiful song.
I did, and I missed it. Oh God. Jeez. I should be really upset with my internet.
You were frozen, so I sung a song from Frozen.
You were frozen too, so I couldn't hear you singing a song from Frozen. Okay. All right. So you asked me what I compared it with. It had nothing to do with the fact that there was an n in the top. You could compare it to n over n squared. That's a bigger denominator, so it's going to be a smaller fraction. But it's on the wrong side of the inequality. If something diverges and it's bigger than something else, that something else can still converge. You have to have a divergent, the one you're looking at has to have a divergent under it before you can say it diverges. If this had been convergent, then anything under it would also converge. So you got to have it going in the right direction. What I had said was that the best test to use was the limit comparison test here, because you know that 1 over n diverges, and if you put that series over that series and inverted and multiplied, you get a 1, so it means they both diverge. That's what that one was all about. Does that answer that, Alexis? You see what I'm saying?
I see what you're saying, but I feel like I've done it before, and I don't know. I think I'm just stupid.
Well,
I don't know. It's probably a bad habit, honestly.
Well, when you're making a comparison test, if you want to make any conclusions, here's what they look like. If you have a converge bigger than something, then that's got to converge. Okay? If you have a diverge bigger than something, that does not mean anything about that one. You don't really know. You don't really know. On the other hand, if you have a diverge less than something, if something's bigger than a diverge, it's going to diverge too. So that's sort of what that looks like. Okay. The last one was just a little picky point that I made. When you use the nth term divergence test, you're using it on a positive term series. This was not a positive term series. It was actually an alternating series. And it's part of the alternating series that failed here. The alternating series has to have the an go to 0. It kind of looks like the nth term divergence test, but it's just the first point of the alternating series test. So it's what this is doing is once you find out, since this is an alternating series and it doesn't satisfy the first point, which means this thing has to go to 0, and it didn't, it went to a half, then we say it diverges by the alternating series test, not by the nth term test. Okay.
See, with this one, I was confused because I didn't know if you wanted us to show the ratio test.
No, the ratio test in that one doesn't work very well. I mean, you could have used the ratio test there, but the ratio test really is kind of for times when you'll get things dropping out. And if you use the ratio test on this one, you'll get n plus 1 cubed and another n plus 1 cubed there, and things don't drop out very nicely. That's kind of why when you use the ratio test, okay?
Because I literally was going to do that, but I didn't.
Okay. Actually, if you use the ratio test on this, and I think somebody might have, that they got it equal to 1, and then that means it's inconclusive. I think that's what happened on that one. But
yeah, I was just confused because I was like, if it's inconclusive, I proved it. I don't know. I thought I proved it by using the nth term test.
Well, the nth term test really is for positive term series. But
okay.
Yeah.
So because it had negatives in it.
Yeah, if it had negatives in it, then you use the alternating series, and you used the alternating series test. If that thing doesn't go to 0, you just say it didn't pass the alternating series test because it didn't go to 0. Okay, so that was sort of picky on my part, but that's what you're really doing there.
Okay.
All right. Anybody else? Okay. So last night you worked on those power series that weren't centered at 0, and you had to find the interval of a convergence, and you were using ratio test again, and then you had to test the endpoints. Does anybody have any questions on any of that?
All of them, because I could not do either. Like, it's just the simplifying part. I feel like I keep messing up. Like, one of them,
You got one. Let's look at one. Let's look at one then and carry it through. And you see one you felt like you were messing up on, you want me to look at?
11.
11? All right, let's do 11. 11 looks pretty good. Let's do 11. Okay, so this is 11 on the power series. In the power series station, it's 572. Is that the one I want? 11. Yeah. Okay. So it looks like n plus 1 over 10 to the nth. N plus 1 over 10 to the nth. And it's times x minus 4 to the nth power. Okay. So this is a power series centered at 4. So my C is 4 here. I'm going to use a ratio test on it. It's going to be the limit as n goes to infinity. You know what, guys? I don't even have to use the absolute value here because this doesn't even have any negative terms in it. I'm not even going to put the absolute value there. The absolute value gets rid of negative terms, so it is absolutely convergent, okay? Because this is a positive term series. But it's not one that's easily compared, and it's a power series. We use ratio test on it. So I'm going to get n plus 1. First of all, I'm going to plug in n plus 1 everywhere here. So that'll be n plus 2 over 10 to the n plus 1 times x minus 4 to the n plus 1 all over the series itself. N plus 1 over 10 to the nth times x minus 4 to the nth. I'm going to invert and multiply here. So that'll leave me with a 10 to the nth on top and the n plus 1 and the x minus 4 to the nth on the bottom. All right, so that's what I got to simplify right there. All right, so Alexis, your question, do you see how I'm doing it all? I'm putting in the n plus 1s and so forth?
Yeah, I think like from the beginning, I didn't add, like I said n plus 1, and then I said the plus 1 on the outside. So I ended up canceling the n plus 1.
Oh, no, you're putting the n plus 1 in the place of this, so it ends up being n plus 2. Okay, so let's look and see how it simplifies. It's the limit as n goes to infinity. 10 to the n over 10 to the n plus 1 leaves me with a 10 to the 1, because you can break this down into 10 to the n times 10 to the first. So those two go. X minus 4 to the n plus 1 over x minus 4 to the n leaves me with just an x minus 4. Okay. You know, I'm going to recant on, I do need the absolute value in the end to find the convergence. So I'm going to go ahead and put that there. Finally, what's left is n plus 2 over n plus 1. N plus 2 over n plus 1. Now, I can take out the x minus 4, and that's over 10. I can just take that out. It doesn't have any n's in it, so this is not going to affect this. And then take the limit of that. And what's the limit of that?
1.
1, okay. So the ratio test says this thing converges when that is less than 1. I'm going to multiply both sides by 10. And that'll say x minus 4 is less than 10. And that says x minus 4 is less than 10 or bigger than minus 10. That's going to be my interval of convergence without checking the endpoints yet. Add 4, I'll get 14. Add 4 here, I'll get minus 6. If you look on a line here, you will see that if I go from minus 6 to 14, halfway in between that is 4. It's 10 units away from minus 6, and it's 10 units away from 14. So that's why we say it's centered at 4, and that's what should happen when you get one of these things. So in there, everywhere in here, it converges. I've got to test 14 and test minus 6. Let's see what the series was. The series was n plus 1 over 10 to the nth. Series was n plus 1 over 10 to the nth, and then 10 to the nth. And then it was, it had an x minus 4 to the nth in it. So I'm going to put in 14. If I put in 14, that's this endpoint, I'll get 10 to the nth. So there's a 10 to the nth right there. So I'm checking 14 now. The 10 to the nths cancel. Does that series right there converge or diverge? Diverges. And this is because of the nth term divergence test, okay, guys? That limit does not go to 0. It goes to infinity. In other words, it does not go to 0. This thing does not have a chance to converge. So you're not going to include that endpoint. Let's plug in minus 6. If I check the minus 6, I'm going to wind up with the series n plus 1 over 10 to the nth. And minus 6 here will make this minus 10 to the nth. So I put in the minus 6 right there for x. All right, let's look at what happens here. I'm going to get n plus 1 over 10 to the nth. 10 to the nth. This, I suggest we write this as minus 1 to the nth times 10 to the nth, because 10 is minus 1 times 10, and I can sort of separate the two. And I kind of need to do that because it'll make this cancel out here. Does everybody see that?
Yeah.
Okay, good. So I'm gonna cancel those out. I end up with the sum here, this series that says minus 1 to the nth times n plus 1, and that is an alternating series, guys. However, does that alternating series converge or diverge? What have I got to check about? What's alternating series tests say I have to check? That thing right there. I need to do decreasing in this thing, but if one of them fails, the test is going to fail. That thing goes to infinity. So it fails the first part of the alternating series test. So it fails that. So actually, neither one of these points are included. So your interval of convergence is minus 6 to 14. Okay, minus 6 to 14. Okay, does that look okay for that one?
Mm-hmm.
Okay. All right, I'm gonna do something a little different today. Not different, but it's actually it's the next section. And I don't know if I'll get it all the way through it today, but I'm gonna look at at least part of it today. I think we're like a day behind on the series. Now, what I'm gonna do tonight is post a quiz on the ratio test on these things right here, and it'll be due by the end of the day on Friday. Okay, by the end of the day on Friday. Just get it to me before Saturday morning. That's all I ask. Okay, so I'll go ahead and post that. Lexus, yes.
So back to the other problem. Whenever like there is like I guess a number that's already being added to it, and we should just go ahead and combine it. Like if it was like n plus 2, I'll still say like n plus 1 plus 2, which is n plus 3.
Yes, exactly.
Okay.
Put it all in the parentheses and combine it.
Yeah. I canceled it out, and once I canceled it out, it just went to infinity. I was like,
yeah,
wow,
yeah, no. You put the n plus 1 in. If you got an n plus 1, say you got an n plus 2 in parentheses, you're going to put an n plus 1 in the place of the n, and then it'll be n plus 3, like you said. Okay? Whoever's back there standing behind you. Okay.
She needs to leave. Like, I don't know what she doing. It's annoying.
Okay. So, so today I want to talk about what we call power series representations of functions. And we've already talked a little bit about this, and this section that I'm going to do right now, part of it depends on geometric series. And I want to look at what we mean by a power series representation of a function. We already kind of looked at one of these. If you look at this thing right here, if you write out the terms will look like 1 minus x plus x squared minus x cubed plus x to the 4th. It's pretty clear here that what you've got is a geometric series where R is minus X, okay? You see you can go from one to the next with minus X. And we know that that converges when the absolute value of R is less than 1. And actually, if we had seen that and realized it was a geometric series, we would have known via a different way. I mean, we could have used the ratio test on it, but it does turn out that it's convergent between -1 and 1. You can see that two different ways, like this, or the fact that it's a geometric series. Now, the nice thing, and then of course, if we did it with the ratio test, we'd have to check 1 and -1, and both of those endpoints diverge. So this is the only place X in between -1 and 1 that this thing converges. But the nice thing about seeing it as a geometric series is you know that the sum of a geometric series is A over 1 minus R. A over 1 minus R. So if you can get that sum for one of these series, you say, oh, well, that's the way, that's what we call the series, the series representation of that function. So tell me what A was in this. We already know what R was, guys. R was minus X. So what's A in this problem? 1. So the sum in this series right here is 1 over 1 minus, and we said R was minus X. That's how we got from one term to the next. So minus a minus X, and we get 1 over 1 plus X. So what that's saying is that that's basically this series right here is the series representation of that function. And I showed you something like this the other day where I said, well, what if you want to evaluate that function at 0.2? Well, you could evaluate it at 0.2 and get a value. You could also plug 0.2 into the series, and the further down you went in the series, the closer it would be to whatever this value was. As long as your R was in between 1 and -1. Those are the things where this series represents that function. Okay, and it's all because we saw it as geometric. All right, now, if I had just asked you to show that thing converges, you could have written it out and said it looks geometric and told me where it converges, or you could have used the ratio test on it and told me the same thing. Okay. So suppose I had this. Suppose I said, how about going the other direction? What if we know that that's some function right there? We just call it f of x. And I wanted to know, was there a series that went with that that would converge to that thing? So what we're going to try to do is we're going to put it in geometric series sum form. So, and remember that's A over 1 minus, I really meant R here, but that's, in my last problem it was X, but the sum of a geometric series is A over 1 minus R. So I'm going to try to put this in that form. And first and foremost, I need a 1 right there, okay? And then I'm going to try to stick it back in the series. If I'm going to get a 1 right there, I need to do something about this 3. And what I'm going to do is divide that by 3. But if I divide that by 3, I'm going to have to divide everything else in there by 3. It's like dividing the whole numerator by 3 and the whole denominator by 3. So that's what I did right here. I divided everything by 3. Now, if you look at it now, it looks like 2/3 over 1 minus x over 3. Now, that looks like the sum of a geometric series, where A is 2/3 and R is just this thing, x over 3. All right, R is x over 3. And again, I did that because I was trying to put it in this form right here. Now, I can write it as a series. Suppose we looked at a geometric series. Guys, a geometric series looks like that. And this is a sum of a geometric series where A is 2/3 and R is x over 3. So I'm going to write the terms out and see what I've got. A is 2/3. The next one, A is always on all these terms. If I want to get my R is x over 3, I'm going to multiply by this 2/3 by x over 3, and I get that. If I want to get the next one, I'll multiply that one by x over 3, and I'll get x over 3 squared. What would the next one be, guys? What would the next one be?
X over 3.
We got a 2/3, and we're going to have x over 3 to the third there. Okay. So in other words, I found out what that function had to have in terms of the sum of the geometric series. All right, in terms of the series. Now, if I wanted to write it as a series, I just look and see what happened. I had a 2/3 in everything. So I wrote that 2/3 down. And then every time I put in an x over 3, that's what I multiplied by. So I put in x over 3 to the nth. Let's see if it works. Now I do need to start this one at 0 because I do need the 2/3. So if n is 0, anything to the 0 power is going to be 1. So I get 2/3. The next one's going to be 2/3 times x over 3 to the first. And then 2/3 times x over 3 squared, and so on. That's the geometric series whose series, well, I'm going to ask you one other question then. If R here, if is x over 3, tell me where this thing will converge. Where does a geometric series converge?
Where R is less than 1.
Less than 1. So I would have absolute value of x between 3 and -3. So this thing right here, this function that I started with, 2 over 3 minus x, the series representation or the sum of that series for any x, and you know what, I should not have put in the, here, I should not put that in, okay. This is the series representation of that function for everywhere it converges. It's almost like this is the domain, okay? This thing is the domain. Now, if R is 1, you end up with just a string of constants to add. It will diverge at both -3 and 3 here, okay? Because with a geometric series, it has to be less than 1.
Why would it be written this way?
Okay, I did this today in differential equations. There are equations you cannot solve. You can't solve them straight up with different things in them, but you can solve them using series representations. I don't know how to, again, when you're learning how to use the two tools in Calc 2, but series are nice ways and faster ways for computers maybe sometimes to compute things. But there are things you can only solve with a series representation. And what we need to know is where it converges. It's like this is the domain, and that's what that converges to, and that's the series that it represents.
So the domain is the x.
The domain is where it converges. Yeah, the x point, okay? Anywhere outside this isn't going to work because this is going to diverge, and it won't have that sum. That's what you're looking at. So for 5, this is no good. It diverges, so you're not going to be able to estimate it with a power series representation there.
And the other things like the function.
Yeah, this is the f of x.
Okay.
So that's the power series representation. This thing right here is the power series representation of this function. It's represented. Okay. It's represented with the power series. Okay.
Okay, I got it.
Okay, let's do another one. Suppose we had this one. 4 over 2 plus x. It kind of looks like a geometric series, but again, one thing I need is a 1 right there. So the first thing I'm going to do is divide everything by 2. So I divided the 2 by 2, the x by 2, and the 4 by 2. Also, I need a minus there. That's not too hard to deal with. I'll just write that as minus a minus. So what that says is when I crank all this out, there's the 2. There's 1 minus this. My R here, guys, is minus x over 2. And my A is 2. So what I know, a couple of things, is that this is under certain circumstances, This is a convergent sum. This is a sum of a convergent geometric series. Okay, let's find out where it converges. Your R is minus x over 2. Here it is right there. That's the 1 minus x, or a over 1 minus r. If I take the absolute value of that, I get the absolute value of x over 2. The minus goes away there. It's less than 1. If I multiply through by 2, and I said it less than 1 because that's where geometric series converge, here is where I can find a convergent series that is a power series representation of this original function right here. All right, now let's put it into the form. The form is a r to the n. So I'm going to put in my r, which is minus x over 2. The 2 was, I could pull, one thing you can do is pull the 2 out of everything. All right, the 2 is going to be in every one of these. So that's a, and then pull it out. And what you'll see if you look at the terms, the first one will be that thing to the 0. So that first term will be 2. Again, guys, there's a 2 in every one of these. You can pull the 2 out and write this as 2 times 1 over that and put the 2 in front. But then you'll get this. If you multiply by minus x over 2, you'll get x squared over 4. Then you'll get minus x cubed over 8, and so on. So here's the power series representation of the function f of x equal 4 over x, 2 plus x. And that's how I wrote it. And it's alternating. Sometimes you'll see them write this differently. You'll see them take the 2 out maybe because it appears in everything. And then you might see them take the minus 1 to the n out and leave an x over 2 here. It's more clear that it's alternating there. Okay, that's an alternating series that converges to this function in that range. That's its domain. I should not have said range, but I was using it in a street language kind of form. All right, now let me show you, here's what that means. Let's pick a number here. Let's pick 1. What's f of 1 here, guys? Tell me what f of 1 is.
4/3.
4/3. And 4/3 is 1 1/3, which if I look at it, it's 1.3333, blah, blah, blah. Okay? This is a series representation of that. If I let x be 1, because it's valid between minus 1 and 1. So if I were to put 1 in here, 2, sum n equals 0 to infinity of minus 1 to the nth times 1/2 to the nth, and you started looking at all the terms, for instance, here are some of the terms right here. I pulled the 2 out. It would look like, if I let n be 0, it would be 1. If I let n be 1, it would be minus 1/2. If I let n be 2, it would be plus 1/4. You kind of see what's happening here. If I let it be 3, it would be minus 1/8. If I looked at the sequence of partial sums here, for instance, the first one, and I'm going to have a 2 here, but the first one would be 2 times 1. So that's 2. The next one would be 2 times 1 minus 1/2. Let's go into that series. So 1 minus 1/2 would be 1/2. 2 times 1/2 would be 1. If I keep doing that, these will bounce back and forth, but they'll get closer. If I look at the sequence of partial sums, it'll get closer and closer to this thing right here. So I could estimate what f of 1 was very well by going way out in the series. Okay, if I went way out in the series and plugged in 1 to this, that whole series would be getting closer and closer to 1 1/3. Okay.
Wait, so there's no x in?
No, I picked an x to show you what was happening here. I said, suppose x is 1, then the value of the function is f of 1 is 4/3. Okay. What it says is
about the other one.
Yeah, and if you let x be 1 in the series, then the more terms you add on and add them up, you'll get closer and closer to this.
Okay.
You get the same, this will converge to that, okay? All right, let's try another one.
Why is the n squared?
Say that again.
Why is it squared? The x over 2.
Right here, it's an n. That's my bad, thank you. That's, it's an n.
Oh,
It's an n, sorry. And they make a sharp point pen that doesn't destroy the screen of the iPad, that'll be good. But right now it's this mushy thing and I can't write with it. It's an n, it's an n. Okay, okay. All right, let's do another one. Notice that both of these were centered at 0. Look at that series right there. You had an x to the n power in that one. The last one that I did also had an x to the n power. What if I wanted to center it somewhere else? Get rid of this. So suppose I wanted to take this one right here. There's an f of x. And I want to see where it converges around another place. In other words, centered at another spot. We saw that in the power series. And suppose I wanted to center it at 1. If I wanted to center it at 1, I would need powers of x minus 1 in it, guys. Anybody agree with that? That's what we did with all those power series in the last section. So here's what I'm going to do. I'm going to say, I need an x minus 1 here. So I'm going to make an x minus 1 there by taking a 1 away from that. But if I take a 1 away from that, to make things balanced down here, what would I have to do? If I took a 1 away in the denominator to make it balanced, I'd have to do what in the denominator? What else? Somewhere else in the denominator.
add 1.
Add 1, exactly. All you chemistry guys ought to be able to do that, right? You got to balance the bottom, okay? So you got to make it ultimately the same, but you're putting it in a different form. So what we've got now is 4 over 3 plus x minus 1. Now, guys, if I wanted it centered at 2, I would subtract a 2 and add a 2. If I wanted it centered at minus 1, I'd put a plus 1 and subtract a 1. I just make what I need right there and balance it with the other stuff down here. So if I look at that now, it looks like this. And if you multiply it out, it looks like the original. I'm just screwing around with it, okay, to make it look like the way I want it. Now, what does a geometric series look like? It has a 1 right here. So the next thing I need to do is sort of what I did on the last one, which is do what to everything in here. If I want a 1 right here, what do I need to do? Divide everything by 3. I can't just divide that one by 3. I got to divide this by 3, and that by 3. So that's what I did in the next step. I divided everything by 3 because I needed a 1 there. Okay, so 3 over 3, 3 over 3. I mean, that thing over 3 and that thing over 3. That's what I got right there. Now, I contend that it almost looks like a geometric series. It's got an A. It's got an R there, sort of, but what's wrong with it? There's one thing wrong with it, and what is it? What's the geometric sum look like?
Oh, the plus.
Yeah, the plus is bad. So what I'm going to do is write it as minus a minus. And I'm not going to distribute the minus through there, but minus a minus will allow me to do what I want. So now what you've got is this is A, this is 1 minus, and this thing right here is R. A over 1 minus R. All right, let's keep going. So that tells me, again, that A is 4/3. R, and I'm going to write that down here, R is minus x minus 1 over 3. And this thing will converge where the absolute value of that's less than 1. Let me play that out, and then we'll write the series. Because once I write the series and know where it converges, I've done everything. This will be absolute value of x minus 1 less than 3. Now, because the absolute value of minus 1 here, guys, is just going to be 1. So it ends up being the absolute value of x minus 1. I multiply both sides by 3. That means that x minus 1 is between 3 and minus 3. And that means x is between 4 and 2. Did I add that right? Let's see, I added 1, I got 4, minus 2, minus 2. So when I look at that, is it centered at minus 1? Doesn't look right. Oh, doesn't look right there. Hang on a second, guys. This one was supposed to be centered at 1. I'm sorry. This says it's right. It's centered at 1. Okay. So it's 3 units away from 4, and 1 is 3 units away from minus 2. This is the interval of convergence here, guys. This is where this new series I'm writing is going to converge. It's also known as its domain. So I'm going to write the series now. A is 4/3. My n is my r is minus x minus 1 over 3 to the nth. That's my r. I raise it to the nth. You can do a number of things here, guys. Sometimes they'll put the minus with the 3 so they can have a clean power on x minus 1. And then sometimes they'll take the minus 1 away here, and away from here, and write those separately. But there's the power series that I was looking for, the power series that is a representation of that function up there that I started with. So somewhere up here. That one right there. And it will converge in between minus 2 and 4. Okay, I'm going to do one more. Again, you just need to identify your A, your R, you put it into this form for a geometric series, and you've got it. You didn't play with it. You can put it in any form you want there. All right, this one looks a little different. This will be the last one we do. Next to the last one. I'm going to say a comment about one more. It doesn't look like it's in geometric terms. I need a 1 here. So I'm going to divide everything by 2. So that's what I did. And now it looks like my r is x squared over 2. And that's okay. When you look at the series, we'll see that that's what you're going to have to multiply by every time from going from one term to the next. So when I write the series, the a is 3/2. I can bring it in or I can leave it out. R to the nth will be x squared over 2 to the nth. You can start writing powers of this out and you'll get a series there. Now, r has to be r, which is x squared over 2 here. Absolute value has to be less than 1. That says x squared, absolute value of x squared has to be less than 2. And that's the same place where x will be less than 2. So it'll be x less than between 2 and minus 2. Okay. So you do that. One other thing, what if we had to do this one? What if we had to find a power series representation of that function right there to begin with? Boy, it doesn't look much like I'm going to get that in any form that looks like a geometric series. However, if I use partial fractions, this is where this is popping up again, and break it down, it looks like this. And I think I can rewrite both of those. This one, all I have to do is put a minus in front of it to turn that around, and then r is x, and a is 1. This one, I just have to turn it around and write minus a minus x. And it converges between 1 and minus 1. So the sum is going to converge between minus 1 and 1. And then when I write them as power series, they look like that. Now, let me say a quick word, guys. Because they both converge in the same place, the whole thing will converge in the same place. In other words, between 1 and I think it's going to be between 1 and minus 1 here. But if one of them had a different convergence, if one of them converged for x is between 2 and minus 2, and the other converged between 4 and minus 4, what's the biggest interval both of them could converge in?
Minus 4 to 4.
well, this is the biggest interval, and this is divergent outside there, so we really have to hang with the smaller one. Okay, we'd have to say the smaller one, because otherwise this one wouldn't converge if I tried to make it as big as that in certain spots. So if they have two separate intervals of convergence, you just take the smaller one, or the overlap, or whatever. Okay, so here's what I think. I put this on your. I think I put this on on your Moodle, on the Moodle sheet. I haven't finished this section yet. I'll take it up again tomorrow. But it says take these, make them look like geometric series. One of them uses partial fractions. This one actually, you don't have to use partial fractions on this, guys. You could let your R be x squared, but you could do it in terms of partial fractions. Do what I was doing to these series above and find the power series that goes with those functions right there, okay? That's all I want you to do on the homework. I have no idea what's on the, I think I was a little behind anyway, but I think I did write those on the assignment sheet. So just see if you can do to those what I did up here. I will post the quiz on power series tonight, and I want you to turn it in by Friday evening, Saturday, whatever. Make sure it's in my box by Saturday morning, okay? That's about the time I'll need something else to grade. Okay. Questions? What's that?
Wait, what's due for today?
There's nothing due for today, but this is the homework for today. Okay. That's the homework right there, and it's on, guys. It's typed on the assignment sheet. Okay, you can write them down right here, but I think I typed exactly the same things on the assignment sheet. Tierra, you had a question.
So are we not supposed to do that quiz that's on Moodle right now?
Oh, it's already put it up there. Oh, good for me. It's not due until Friday or Saturday, okay? Yeah, it's up. The power series one's already up there. I forgot, I did write that for you guys, didn't I? I'll look at it and see if I still like it. I'll let you know. But yeah, that's the one I want you to do.
Okay.
Two quizzes or one quiz?
One. I just have forgotten I had written it ahead of time. I hardly ever do anything way ahead of time, so you know, who knew I forgot. Okay. So
are we not doing the ratio one?
You do the ratio test. Did I put it on there? You haven't done. I want you to do the guys. I tell you what. Let me look and see what I've got on Moodle. Okay, and I'll put the ratio test one, you know, due whenever, Friday or something. I'll put the other one, this stuff right. I don't think I've done power series representations of this. This is not a quiz, guys. This is homework. So yeah, I think the only one on there is the ratio test one. So that's the one that's due Saturday morning. Yeah, that's the one that's on there. It's power series. It's power series. That's what it should say on it, power series. Okay, I'll double check it, but I think that's.
Okay, I see what you're saying. I just thought because there was just, I heard ratio, quiz, like, and then the power series. I thought those were two separate ones, but they're just.
No, you do the power series one, and you use the ratio test to do power series. Okay, that's all. That's why we're getting confused.
Okay.
Okay, all right. Everybody okay with that? Try these tonight. Play with these tonight, because it's kind of interesting to manipulate them and see what the series is. Okay, and we'll start there again tomorrow. Okay, I'll talk to you tomorrow unless somebody's got another question. I'm hot. It's gotten hot today. Okay. All right. I'll see y'all later. Bye.
I'm trying to leave, but
I'm trying to leave too.